Good morning, students. So let's start our the next lecture. So in this lecture, we start the equivalence relation. Last lecture, we studied about the properties of relations, in which we have the reflexive relation, symmetric relation, asymmetric relation, antisymmetric relation, transitive relations, like that. So now we studied about the equivalence relation. So what is the equivalence relation? A relation R on a set A is called an equivalence relation, or we say that RST relation if it is R means reflexive, S symmetric, and T transitive. So, if any relation satisfies all these properties, reflexive, symmetric, and transitive, then this relation is called the equivalence relation, right? So, the three properties are, we earlier studied about the reflexive. What is the reflexive? If A belongs to R, for all A belongs to set A, that is the reflexive. Second, what is symmetric? If AB belongs to R, then that is BA also belongs to R, then it is the symmetric. If AB and BC belongs to R, then AC belongs to R. So it is the transitive property. If any relation hold all these three properties, then that relation is called the equivalence relation. So now take an example for this, what how to show that the relation is the equivalence relation. So if R, here we have the relation that is the set of integers z, so defined as the ordered pair sets xy, where x and y elements are the integers, and the relation is defined by x minus y is divisible by 6. So here we have to prove that the relation R is the equivalence relation. So for this, to prove the equivalence relation, first what we do, first we have to prove the this is the reflexive. So for reflexivity, let's take an element x that is belongs to the integer z. So here it hold this property, x minus x is divisible by 6. X minus x, what is x minus x? X minus x is 0, and also 0 is divisible by 6. So we can say that this is the this holds the property of reflexivity, means R is the reflexive. Now second we have to show that here it is the symmetric. So for symmetric, we have that if x is related to y, then y is related to x. So we have to prove this. So first let's take that x is related to y. So we have the relation is x minus y is divisible by 6. And if x minus y is divisible by 6, then we say that minus negative x minus y is divisible by 6. Yes, we can say that because the x, y are the sets of the integers, and integers we have the positive and negative both. So, if positive part is divisible by 6, then also the negative part is also divisible by 6. So, we can write this x minus y, we can write that minus xy minus y is also divisible by 6. And this, if we multiply this minus in our braces, so we have that y minus x. After solving this, we get y minus x is divisible by 6. So if y minus x is divisible by 6, then it means that y is related to x. So it is a symmetric. Now, third condition, we have to show that this is the transitive. So for transitive, we have to take the three elements x, y, z in our set A. So if we take x is related to y and y is related to z, so we have to show that x is related to z. If we can show that x is related to z, then we can say that it is the transitive. So we have x related to y, it means that x minus y is divisible by 6, and y is related to z we have. So we can take that y minus z is divisible by 6. Now these things we have. So from these things we take that if one number is divisible by 6 and the other number is also divisible by 6, so always it is true that the sum of those numbers is also divisible by 6. It is always true. So if we adding these numbers x minus y plus y minus z, so the summation of this is also the divisible by 6. Now when we solve this, then we get x minus z is divisible by 6. And if x minus z is divisible by 6, it means that x is related to z. So now it is the transitive. So here we show that it is this relation, given relation is reflexive, symmetric and transitive. So we can say that this relation R is the equivalence relation. So like that you have to prove that any relation is the equivalence relation or not. So now, like that, we take the second example. Here, our here we take the two real numbers theta and phi. Here we take why theta and phi, because here we use the angles. So we here take theta and phi elements, that is theta is related to phi. In which relation? The relation is that say secant square theta minus tan square phi is equal to 1. So we have this relation of R. Now show that R is an equivalence relation. So we start here. First we have to check that this is reflexive or not. So first for the reflexive, we have to take only one element. So we take here the theta. Theta is related to theta, means here we have to put theta only element. So secant square theta minus tan square theta equal to 1. Is it true? Yes, it is true, because earlier you studied about in your trigonometry that secant square theta minus tan square theta equal to 1. So it is a reflexive. Now second thing is symmetric. So we have to show that it is symmetric or not. So for symmetric we have to show that theta is related to phi, then phi is related to theta. So first we take theta is related to phi, means our condition is that secant square theta minus tan square phi equal to 1. Now we solve this. We know that secant square theta is 1 plus tan square theta. So and tan square phi, we can write this secant square minus phi minus 1. So now 1 plus tan square theta, and when we open this is minus secant square phi plus 1 equal to 1. So after solving this, we get secant square phi minus tan square theta equal to 1. And this condition shows that phi is related to theta. So this is the symmetric relation. Now next we have to show that it is transitive or not. So for transitivity we have to take the three elements. So here we have to consider the three angles theta, phi, and next angle we take here the psi. So if theta is related to phi and phi is related to psi, then we have to prove that theta is related to psi. So now we have to take our conditions here. Theta is related to phi, it means that secant square theta minus tan square phi equal to 1. It will have. Now if phi is related to psi, it means that secant square phi minus tan square psi equal to 1. So now we have to take both these. So another we have to apply here that thing that the summation of these, if we add these things left part and the right part, then we get secant square theta minus tan square phi plus secant square phi minus tan square psi, that is equal to 1 plus 1 2. Now we solve this. Now secant square theta uh, plus This is secant square phi minus tan square phi minus tan square psi equal to 2. And secant square phi minus tan square phi, it is equal to 1. We know that. So now secant square theta and this become minus tan square phi, it is equal to 1. So for this condition, we say that theta is related to psi. It means that our relation is the transitive relation. So now we show here all the properties, all these three properties, reflexivity, symmetricity and transitivity. So this relation is our the equivalence relation. Now it's clear what is the equivalence relation and how to show that any relation is the equivalence relation. Now let's next take the partial order relation. So what is the partial order relation? A relation R on a set S. Earlier we take the set A, you can take any set. So here we take a set S, and the relation R on this set is called a partial order if it is satisfy three properties, that is reflexive, antisymmetric and transitive. In the equivalence relation, what we have? In the equivalence relation, we have to show that the reflexive, symmetric and transitive, but in partial order relation, we have to show that our relation must be reflexive, antisymmetric and transitive. If this have all these properties, then it is called the partial order relation. So what is our reflexive? Reflexivity is that if A is related to A, for all A belongs to S. Antisymmetric, what is the antisymmetric relation? That is A related to B and B related to A. When? When A equal to B. Now transitivity, A is related to B and B is related to C, then A is related to C. So this is called the partial order relation, and also we can say that a poset, and it is denoted by SR. So now take an example for this. So then here we take the example the greater than or equal to. This is our relation, greater than equal to relation. We have to show that this greater than equal to relation is our partial order relation or not. So partial order relation and our the set S, that is the integer set of integers. So now first we have to show that the reflexivity condition. So reflexive, since for reflexive, since our A element is obviously greater than equal to of A, so for any integer, so we can say that our greater than equal to condition is reflexive. Now antisymmetric, for antisymmetric, since A is greater than equal to B and B is greater than equal to A, when it is possible? It is possible only when R A equal to B. So we say that this greater than equal to is antisymmetric. Now transitive. Since here we have to take the three elements A, B, C of the set, means of the integers, then A is greater than B and B is greater than C when it is possible. So it is true also for A is greater than equal to C. So we say that greater than equal to condition is transitive. So it satisfies all these properties, these three properties. So this is greater than equal to is the partial order relation on the set Z. So this is our the poset. We can say that poset. So today's lecture is completed now. Thank you.